This is the recording for topic 2.2, calculating limits using limits law. So basically, we are going to discuss theorem 1, limits law, and show you a few examples of how this theorem could be applied. The important point that we are going to discuss in this topic is the following. That is, you assume that some functions f, the limit of this function is known. Okay, so say when x tends towards the value of c, the limit of the function is known, and you may have another function f or gx. When c tends to c, the limit of g is m. So assuming the knowledge of the limits of function f and g at c, then these theorems allows us to obtain the limit of another function which is comprised of the function f and g. So basically, in the studies of the limits, what we actually want is the ability to tell what is the limit of some function h when the values of x tends towards c. Okay, so at this point, we are defining the limits of a function at a point c. Okay, so in general, if I give a function, I ask you, okay, these functions, x tends to some number c, what is the limit? So we want to answer that questions. In general, the questions of the limit of some arbitrary function at point of c is kind of not easy. However, we will learn up in this course how would you able to work out the answer for limits like this by using certain rules or certain tools. So we will begin with simple tools. The simple tools that I'm talking about is theorem 1. So you can imagine theorem 1 to be a set of rules 1, 2, 3, 4, 5, 6 that allows you to answer restricted questions of the form where the limit of some function h is expressed in the form of the limit of the other two functions f and g, where these two functions are related to this function h. So let me explain myself better. If you have a function of h that could be expressed in some relationship to the other two functions f and g, where the function of f and g limit at the point c is known, then you can make use of the information of the limit of these two functions to work out the limit of the new function h based on the rules of theorem number 1. Now, in other words, if you do not know the limit of the other two functions, say you don't have a relationship that relates the function h to two functions on which the limits are known, then you can't use this theorem. Okay, so here in this topic, most of the time you would be given, okay, you have a function of f, you have a function of g, and you know the limit of these two functions at a certain point. Then what is the limit of another function h, where the h is expressed as a function of f and g. So let us look at these things a little bit in a little bit more detail. There are actually 6 situations. So first we begin with the knowledge that the function of f limit is known, okay? And the limit of another function, the limit at the point c is also known, and the values of the limit for f and g are are known to be L and M. Okay, so these are the known informations. And say in the first part of the theorem number 1, it says if you have a new function h, where the new function h can be expressed as in terms of f and g, such that h is just the sum of f and g. Okay, so according to theorem number 1 in this topic, it says the limit of the function h of x at the same point of c is then just equals to the sum of the limit of f at the point c and also the limit of the function g when x tends towards c. Okay, so that is what the theorem number 1 sum rule says. So try to understand what is this. It looks like quite straightforward. H equals to f plus g, so the limit of h is just L plus m. I think the important thing that you have to appreciate is that the theorems are asking for the limit of a new function h, right? And the theorem says in order to obtain the limit of the function h when x tends towards c, it is just the same as the limit of f added to the limit of g in when x tends towards c. So here the results of the limit of this new function is obtained based on the information of the function f and g, or the limit of f and g. Okay, so if you know the limit of f and g, then you can know the limit of h if h is just defined to be the sum of f and g. So likewise, if you have another function which is formed by the difference between the two functions f and g, then the limit of h can also be known when x tends towards c is just the limit of the function f when x tends towards c minus the limit of the function g when x tends towards c. So this is just L minus M. So this is what the first two rules says, the sum rule and the difference rule. The third rule is very similar. If you have a new function h which is defined to be the product of a function f and g, then the limit of this function h can be easily calculated to be the product of the limit of f and g at the point x. Okay, so if you write it down, then you say the limit of this function x at the point x tends to c is just the product of f of x tends to c multiplied with the limit of g of x tends to c, or this is just equals to L times M. Then the fourth item in the theorem number 1 is that if you have a function h which is defined to be the product of a constant k multiplied with function f, and if you know what is the limit of the function f when x tends towards c, then the limit of the function h when x tends towards c is just equals to the constant k multiplied with the limit of the function f when x tends towards c, and this is written as f. Okay, so that is what the third rule, the fourth item in theorem 1 says. Then you have also the fifth and sixth item in the theorem 1. So basically it just says if you have a new function called h which is defined to be the ratio of two functions f and g, then the limit of the function h when x tends towards c is just equals to the ratio of both limits of f and g separately in this manner. X over c. I think that is what the theorem was saying. And if the limit of f at c is L and the limit of g at c is m, then given the function h as the ratio of f and g, then the limit of this function at the point x at c is the ratio of L over m, provided that the limit of m is not 0. Okay? If m is 0, then this statement does not hold. Then the last item in theorem 1 is that if you have a function of f and the limit of the function of f is known, is equals to L, then if you have a function of h which is related to the function of f such that h is the function of f raised to a power of a fraction of r over s, where r and s are just two numbers. I think r and s could be any real number, okay, so r and s I think can be any real number. So if h is related to f through this power relationship, then the limit of the function of hx at the point c is just equals to the limit of the function of f at the point c raised to the same power of r and s. I think that is what this item 6 in theorem 1 says. And if limit of f at x equals to c is L, then this is written as r over s. So this is basically what theorem 1 says. It's very easy to understand. So basically theorem 1 tells you how to calculate the limit of a function that are expressed as in terms of the other two functions f and g. It's a very simple example. Say you have a function of x cubed plus 4x plus minus 3. So here this is the function called hf. Okay, I think this is a function of h. So you can consider hx to be the sum of the first function x power 3 add to the other function minus another function. So hx is a sum of 3 different functions. So according to some rule, then the limit of this function hf is just the limit. And let me write down what it says. So you let hx stands with c. The limit in hx at c is just equals to the limit of this function when x tends to c plus 4 times the limit of the function x squared when x tends towards c minus 3. Well, minus, let me be more careful. Okay, so let me write off this one. So this means minus 3. So this is the limit. I would write this as the limit of the function 3 when x tends towards c. Okay, so given this h function as the sum of 3 different functions, the limit of function h can be expressed as the sum of the individual function. And for this particular case, the limit of the function 4x squared when x tends to c is written as 4 times the limit of the function x squared when x towards c. So when I write from here to here, I am actually making use of the constant multiple rule. Okay, so when I write down the limit of h of x equals to the sum of these three terms, I am making use of the sum rule. Okay, so these are a very simple example of the applications of the limit law. Okay, and in order to proceed further, this limit x power 3, the limit of x power 3 is this. Okay, so if I have a function of x power 3, the limit of the function x power 3 when x tends towards c, according to the rule number 6, that is equals to the limit of x with x tends towards c raised to the power of 3. Okay, so that is the limit of x when x tends to c raised to the power of 3. And we have seen in the previous example of 2.1, right? So I think we have discussed this. Say if you have a function of a constant, then it is shown that for a constant, the not a constant, for a function of y equals to x, the limit of the function x when x tends towards any point c is just equals to c. So this is a very straightforward results. So here, when you ask for what is the limit of x power 3, that is equals to the limit of x raised to the power of 3, and this limit is just equals to c raised to the power of 3. So that is the result for the limit of x power 3. For this one, 4 times x limit of x squared, it is just equals to this. Okay, limit of 4x squared, x tends to c is just equals to 4 times limit of x tends to c, the whole thing squared. So when I write down from here to here, I am actually making use of this rule, that is rule number 4, where I separate the values of 4 from the rest. Then when I write down this term, I am actually making use of the power rule. Okay, so that would then allows me to break this into the product of 4 times this, and this is equal to 4 times the limit of x with x tends to c, and this is equal to c squared. So that finish up the evaluations of the limit of 4x squared when x tends towards c. Then lastly, we have the terms of 3. So this is trivial. The limit of 3 is equals to 3 whenever x tends to any values of c. So the h function is the sum of 3 terms, and we have evaluated the limit of each of these terms one by one using the rules that is specified in theorem 1. Now you may find this absolutely straightforward. Why should I spend so much time to express to you that the limit of this function when x tends towards c is just equals to this? So this is the result of the limit when x tends towards c. However, my purpose is to demonstrate to you every single line in my calculation from here to here, and from here to break into 3 parts are not carried out arbitrarily. Every single step that I have done so far are all based on the theorem 1, which is the limit law. Right, so the calculation that is written down step by step here are done based on the rule that is allowed by mathematics. You just don't simply write down things that is not guaranteed or warranted by the law. Okay, so you try to comprehend what I said here. That is, when you do calculation in your mathematics, when you write down a rules or from one step to another step, you ask yourself, are you doing this based on rules that is legal, or you are only basing the steps based on your own feeling, right? So if your steps are not warranted by any mathematical statements, then your steps, your calculation may not be correct. I usually like to give an example. I think it's like this. You have the sine of x divided by n, and what is the values of this? So the answer of this is, I think, is 6. So this is what some people say. So how do you get from sine x divided by n into 6? So I think if you do not follow mathematics rule, you would follow your rule, and you stop follow your rule, then you said this is n, I just cancel the n, then I got six, and x and x is just 6. Therefore, he says sine x over n is 6. So this is definitely bullshit. Why you arrive at this bullshit is because you are carrying out this calculation not based on the rules of mathematics. The rules of mathematics say sine of x is not equals to s times I times n times x. So this is not, the left hand side is not equals to the product of 4 variables. This is to say you have a variable x, then you define a trigonometric function, and the trigonometric function has a name which is called sin. So sin here refers to the name of a specific function, a specific trigonometric function, which reads in the variable x to give you a number called y. So that is the correct way of doing mathematics. So if you understand that sine of x is defined in this manner, then you would not do stupid things like this. I think last time people do this, they just cancel off and then they got this kind of things. Okay, so suffice to say is that the steps that I show here, which is a very simple example of calculating the limit of an polynomial equals to this expression, have to be done following the theorem number 1. Okay, so example number 1, another example of another example. So here is example A, this is example B. So in example B, we have the ratio of two functions, the first function and the second function. So let me try to just try to be a little bit more formal to write down this example. Okay, so I have an example B, and the example B is a function which is defined to be the ratio of, say, f over g. Okay, so here the function of f according to here is x power 4 plus x squared minus 1. So this is x power 4 x squared x power 4 plus x squared minus 1, and g is another polynomial function, x squared plus 5. I have to keep on referring because I don't have very good memory. So this is the questions, and you are asked to calculate the limit of the function h when x tends towards c. Okay, so the answer or the steps to get the answer is actually quite straightforward. But I'm not going to write down the answer for you, but I'm going to show you the actual process of arriving at the answer. So before you proceed on, just try to realize that h is the ratio of two functions. Therefore, the first step to proceed is to first consult the theorem. So here the theorem to be consulted is this. That is, you have to look at the quotient rule. The quotient rule says if you have a rational functions, then the limit of the rational function is just the ratio of the individual function. So here, this is to say this is equals to the limit of the function f c divided by the limit of the function g when x tends towards c. Okay, so I'm very careful. So I write down these equations. So this is the equation that is given. So I write down these statements by referring to rule number 5. Okay, so I'm definitely correct because I'm just writing down the rule based, the equation based on the rule. So the next thing I want to do is that I want to then work out what is the limit of this function. Okay, so again, the limit of the function for the limit of the function of f when x tends towards c is equals to this, right? So the fx is comprised of 3 different terms. So I'm going to write down the equations by using the sum rule. Right? The sum rule says if you have a function which is comprised of the sum of 2 different functions, then the limit of these functions is just the sum of the individual limit. So here I have x power 4, x squared minus 1. So here this is equals to the limit of x4, x goes to c, plus the limit of x squared, x going to c, minus the limit of x going to c for the function 1. Okay, so then I continue to write down this is equals to the limit of x when x tends towards c and raised to power 4. And here is again limit of x goes to c, whole thing square, minus, okay, minus what? Minus the limit of a constant. Okay, the limit of a constant is just equals to the constant itself. So when I write down from here to here, when I write down these equations, this refers to this term, I am actually making use of, again, the quotient rule, where I assume, sorry, not the quotient rule, the power rule, where here I assume s to be 1 and r to be an integer of 4 and integer of 2 respectively. Okay, so remember, I write down this term by referring to a law. I also write down this term to represent the limit of this function based on the law of theorem number 1. And now I got almost to the answer. That is the limit of x when x tends towards c is just equals to the values of c, right? And then raised to power 4 plus c raised to power 2 minus 1. Okay, so here I'm making use of the fact, of the known fact that the limit of x when x tends to c is equals to c. And this again is the result that we have already discussed in the previous section, that the limit of a linear function is just equals to the values of c. Okay, so here you realize that the answer to these questions requires you to make use of this result, and this is a result that is obtained in the previous subtopic. So this will always happen in our ZCA 110. You would often have to make use of the result that you have proven in the previous sections, and you need to use these previous section results in order to use it in these sections, right? So if you are not able to recall the previous result that you have already proven, then you will have a hard time for this course. So here we have just shown you the limit of the functions is equals to this. So you can apply the same thing to the limit of g. Okay, so you can also obtain the limit of the g function in a similar manner. So the limit of the function g when x goes to c is just equals to x. So the g is x squared plus 5. So the limit of x squared plus 5 is simply equals to limit of x raised to a power of 2 and x tends towards c plus the limit of 5 with x tends towards c, and then you would just write this as c squared plus 5. And obviously, of course, if you are very smart, when you look at the expression of gx, which is x squared plus 5, you don't need to write down this one, but you can just write down the final answer without even writing this down. But I'm writing these steps for you to aware that when you go from here to here, you are actually making use of the rules that is mentioned in theorem 1. Okay, so having said that, we now can express the values for the function. Limit of the function of f when x tends to c is just this expression. So answer is just c power 4 plus c squared minus 1. And the downstairs, the limit of g at c is just c squared plus 5. Plus 5. So this is just the results for the function of h. This is the answer. Okay, so that is the full solutions to example 1b. It is a very straightforward demonstrations, but be aware the purpose I express and spend so much time in working out all the details here for you, just to make you realize that every single step you write down are warranted by an theorems. Okay, without this theorem, you can't arrive at the simple result as this. Okay, then we have another example of this is the power rule again. So here we have a function 4x squared minus 3. So the results for the limit when x tends towards 2 is just equals to all the steps that is written here. So you have a function of h. The function of h is equals to function of f raised to a power of r over s. Here, the r is 1, s is 2, and the function of f is just equals to 4x squared minus 3. Okay, so this is fx is 4x squared minus 3, and then the limit of the function that we are going to solve is when x tends towards minus 2. Okay, so we have such a function and we want to know what is the limit of hx when x tends towards minus 2. Okay, so this is just the same as the limit of 4x squared minus 3 raised to a power of 1/2 when x tends towards minus 2. So the correct answer or the steps that you can skip a little bit is this. This is equals to 4 times the limit of x tends towards minus 2 squared, okay, minus the limit of 3 when x tends towards minus 2, and the whole thing is raised to a half. Okay, so that is written down based on the theorem number 1, and this is just equals to 4 times x, well, x, no, I think this is equals to, okay, so you look at this one, you have a limit of x when x tends towards minus 2, the limit of x when x tends to minus of 2 is just equals to minus 2, and then you have a square. Then you have a minus limit of 3 when x tends towards minus 2. Right, so this is a constant, so no matter x tends towards any number, the limit of a constant is always an constant, and the whole thing is going to be n squared. Okay, so that is just equals to 4 times 4 minus 3 with 1/2. So this is 16 minus 3 is just It's just some number, right? 16 minus 3 is just 13. So it's just 13 to the square root. So that is the answer. So again, the evaluations of the limit for this function when x tends towards -2 is kind of straightforward. I just thought that you just substitute in number, but you don't really substitute number straightforwardly, but you have to show that this is equals to this, equals to this, equals to this, following the steps as warranted by theorem 1. So these are very simple and straightforward calculations. So we have learned from this theorem number 1 that that this theorem is a very useful tool, right? So the useful tool allows you to obtain the limit of a function h if you know the limit of the function f and g at certain point of x equals to c. Here h is expressible in terms of the function f and g. So here we have some preliminary tools that allows you to obtain the limit of some new function. So we are going to learn theorem number 2 and probably theorem number 3 as well. So theorem number 2 and theorem number 3 and theorem number 1 have some commonality in the sense that these are tools, T-O-O-L tools, that will help you to obtain the limit of some function h. So theorem 1 is a tool that expresses the limit of h in terms of the limit of f and g, whereas the theorem 2 is a different type of tools. It is actually can be considered as the summary, or maybe not summary. This theorem 2 and theorem 1 are actually very much related. So if you put all these theorem 1, the product rules and sum rule, quotient rule and power rule together, then you realize that if you have an polynomial, then the rules number theorem 1, the rules in theorem 1 actually allows you to show that if you have a polynomial in this form, then the limit of a polynomial is simply equals to the values of the polynomial. The values of the polynomial are evaluated at the values of c, right? So this is another very useful tool. So with the theorem number 2, next time when you are given some polynomial function, and then straightforwardly you will be able to write down straightforwardly the limit of the polynomial. And what is the limit of the polynomial function at the point c? It is simply equals to the values of the polynomial evaluated at that point. That's for example, just example. I think here you got example, maybe here. I think this example, say you have a polynomial of order 2, say equals to 2x squared minus x plus 1. Then the limit of P2 x when x tends towards, say 101, it's equals to blah blah blah. Now according to rules number theorem number 1, in order to obtain the limits of the polynomial P2, here you have to sum up and break up this term and sum with this term, sum with this term. So that is of course correct. I think in the previous example ABC, this is what we did as well. For example, in here we show that this is a polynomial. In order to obtain the limit of this polynomial, now you have to break it up using rule number 1, 2, 3, 4, 5. But here theorem 2 says no, you can actually make life much easier. You just simply substitute the values of c into the expressions of the polynomial. That is, so just calculate this number, 2 times 101 squared minus 102, and just look out the number. So this will be the limit of this polynomial when x tends towards a number of 101. So again, theorem 2 allows you to obtain the limit of a polynomial straightforwardly, right? You don't need to do any calculation, but you just slot in the values of x at the point C into the expression of polynomial, then that is the result of your limit. Then theorem 3 is kind of a generalization of theorem number 2. That is, if you set here function of q x to be equals to 1, then theorem number 3 will just reduce to theorem number 2. So theorem number 3 is a generalization of theorem number 2. It says if you have a new function h which is defined or formed by taking the ratio of two polynomials, then the limit of the function h at certain point is simply equals to the values of the polynomial upstairs evaluated as c divided by the polynomial downstairs evaluated at the point c. So here also it's kind of like handy. It allows you to work out, say for example, the limit of this function straightforwardly. If you do not have theorem number 3, in order to work out the limit of theorem number 3, this is what you have to do, right? So in example B, this is a rational polynomial. To work out the rational polynomial, you have to break it down into the ratio of two functions, and you evaluate the limit of the first term, second term, third term, add it up. Then you calculate this one and this one using all the product rule, sum rule, quotient rule. So it's kind of like very lengthy. If you were to refer to theorem 1 to calculate the limits of the ratio of two functions. However, with theorem number 3 that is introduced here, the values of the limit for this can be just simply calculated by substitute the expression of x with the values of c in this polynomial. That will give you the limit of the function. So it's kind of handy, I would say, handy. Then these are the example that will actually tells you, this is an example of evaluating the ratio of two polynomial functions which may appear to be not in existence. Okay, so for example, okay, this is an example of the ratio of the two polynomial. The applications of theorem number 3 into example 3 here have to be carried out very carefully, right? So you would think that here you have a polynomial pq, downstairs is another polynomial, upstairs is a polynomial of p, downstairs is a polynomial of q, and if you are asked to calculate the limit of this p over q at x equals to 1, according to this theorem, it says you just substitute the values of c into the expressions of the polynomial upstairs and downstairs. So if you were to do that, then you think, that means I can just calculate p at 1 and q at 1. That will give me the limit of the functions at x equals to 1. And if you do that, then you get into trouble because downstairs x squared minus 1 is just 0 when you substitute x equals to 1. So you get infinity. So you say, this limit does not exist. But this is not quite true. The reason why this is not quite true is that you are not being very careful. Okay, so just let us try to go through this example a little bit carefully. So let me write it down. Let me try to copy the questions into my whiteboard. It is x squared plus x minus 2 over x squared minus x. Okay, so I have a function h which is equals to the ratio of two polynomial p and q, where here px is the polynomial, qx is another polynomial. Okay, so the px is x squared plus x minus 2. X squared plus x minus 2. Qx is x squared minus x, x squared minus x. Okay, so but you have to be a little bit careful. Now, so let me write it down. P and Q to be like this. X squared minus x, and you have to factor out this one. You have to factor it out. That's become x minus 1. Here is x minus 1. X, I think plus 2. Okay, so that is how the ratio of these two polynomials is expressed as the in terms of the product of the factor. We call this a factor of x minus 1 and a factor of x plus 2, and this is a factor of x minus 0, factor of x minus 1. Okay, so you can't just substitute x equals to 1 into the expression here, right? Because if you substitute x equals to 1, then the whole thing will become 0, right? So if it's 0, then you would have problem, right? So it's 0. If you substitute x equals to 0, then what happens would be that this is 0 divided by 0. Even though x plus 2 is not 0, x is not 0, but x minus 1 will be 0 if you substitute x equals to 1 into this expression. So what I'm trying to tell you is that x in this case could never be 1. If x is equal to 1, then you cannot cancel it off. So that is the mistakes that people would make. They will say, okay, I have x minus 1 upstairs, x plus 2 upstairs, x downstairs, x minus 1 downstairs. Therefore, I see x minus 1, I see x minus, I just cancel it off. That is left with x plus 2 over x. Okay. Now, I think that is possible, that is correct. Okay, so x would never be equals to 1. If x equals to 1, you just cannot cancel these two factors. Okay, so x equals to 1 is never be inside the domain of h. Due to this, you can cancel off x minus 1 upstairs with x minus 1 downstairs to arrive at this statement. Okay, so once you have cancelled off the factor of x minus 1 upstairs and downstairs, then the ratio of p over q is now x plus 2 over x. Then the limit of this function at x equals to minus 1 is then easily calculated to be just the values of x plus 2 evaluated at x equals to minus 1 divided by the values of x evaluated at x equals to minus 1. And this is nothing but just minus 1 plus 2, which is minus 1. Downstairs is just equals to minus 1, and it end up to be positive 1. Okay, so you can't apply, I think I have made some mistakes here. Okay, so let me come back to here. X plus 1, x plus 2, the values is to be evaluated at x equals to 1. Yeah, I'm sorry, I think here this is not minus 1 but 1 instead. Okay, so I'm sorry about that. Here this is equals to plus 1. Okay, so it is plus 1, and this is plus 1, this is plus 1, then you have plus 3, and you have plus 1, so this is plus 3. Okay, anyway, it's a minor mistake that I apologize here. So you would not apply the substitution of x equals to minus 1 straightforwardly into the expression of p over q in the beginning, right? So you have to first make sure that you expand the quadratic functions into the product of their individual factor. Then realizing that x equals to 1 would never, well, realizing that x is never equals to 1 in the domain of the function of h, then you cancel off x minus 1. Like x minus 1, they cancel off. Then you are left with this. So you can then substitute the values of x equals to 1 into the expression of p over q, which is now reduced to x plus 2 over x. Then this will give you the answer for the limit. Okay, so it's a very simple demonstration of the applications of example number 3, right? So before you can substitute straightforwardly the values of x into the p and q, you have to make sure that this kind of situations does not occur. Okay, so that is the demonstration of example 3. So now we are going to discuss another tools. I think theorem number 4. So theorem number 4 is another tool that we are going to discuss in this section. It is a tool that will allows you to obtain the limit of a function given the knowledge of the limit of the other two functions. Okay, so again, in chapter 2.2 here, we study theorem 1, we study theorem 2, theorem 3, and now we are studying theorem 4. All these theorems are tools that allows you to evaluate the limit of a function at a point. So here, the sandwich theorems says if you have a function f which is not known, so you want to know what is the limit of this function at some point c. So you want to answer this question, but you do not know what is the limit of this function. However, if you know that exists other two functions, g and h, such that within some intervals of x, within this interval, say for example between x1 and x2, the function of g is always larger than function of f, or larger, or sorry, here h is always larger or equal to the function of f, whereas function of f is always larger or equals the function of g within some intervals that contain the point c. And furthermore, if you also know the limit of the function g and h at the point c, then the sandwich theorem says the limit of function f at the point c is just simply equals to the limit of g and the limit of h. Here we assume that limit of g and h are the same. So let me explain this in my whiteboard. So here, if we assume there is a function of f, and say the function of f is larger than the function of, here we said it is g, and this is smaller than hf. So, and then it is known that this is true for x that is lying on some intervals of say x1 and x2, and then this x1 x2 contain the values of c, and at the point of c the limit of the function g is known. So is the limit of the function h is also known at c, and both are assumed to be the same. Okay, then if you represent these situations on a graph, then what you can write is that you have say f here, then h is always lying on top of g, and so like h is always lying on top above of f, and g is always lying below g. So these are the relative relationship between h, f, and g. And not only that, the limit of g and the limit of h at the point C are the same. So I think this is not an accurate representation of the relationship between these three. The more accurate relationship between these three actually is represented by figure 2.3. So here, the limit of the function of f at the point C here is then simply equals to the values of L, where the values of L is the limit, the common limit of h and g. So it is intuitively kind of like easy to understand, right? So you make use of the limit of the function of h and g that sandwich the function h to arrive at the limit of the function of f. Okay, let me say it again. In order to find out the limit of the function of a sandwich function f that is always sandwiched between an upper function h and a lower function g, the limit of this f could be obtained to be the limit of f and g at the point C if the sandwich always happen within some region, and the limit of h and g at the point C are the same. Okay, so that is basically theorem number 4. And in order to understand theorem number 4 better, you look at example 6. In example 6a, we are asked to find what is the limit of the function sine theta when theta tends towards 0. So this is a very simple questions. Everyone knows the values of sine theta when theta goes to 0. It is equals to 0, right? But the purpose here is not really to find only the values of the limit of sine theta at 0, but to prove it, right? How do you prove that this is so? It is best illustrate this example by using the sandwich theorem. So as I mentioned in the sandwich theorem, in order to prove the limit of n given functions using sandwich theorem at some specific values of x naught, you need two conditions. The first condition is that you have to find out two functions h and g that sandwich two functions that sandwich the function of f. So we assume h to be larger than f and g to be smaller than f. So try to find if it's possible a function of h and g that is like this, and this is the first condition that has to be fulfilled for some x in some intervals that includes the values of x naught, right? So this is the condition number 1, the existence of a function h larger than f and a function of g smaller than f within some intervals that contain x. And at the same time, there is another condition that has to be imposed on h and g, that is the limit of h and the limit of the function g at this particular values of x naught are the same, right? So if you can find two functions f and g that fulfill this condition, then the limit of the function f at the point x at x naught is simply equals to the values of L, right? So you make use of the knowledge of the limit of function f at h and g at the point x naught to allows you to obtain the limit of the function of f. So here, the function that we are testing is a function of f theta equals to sine theta. So you try to represent this function sine theta on a graph. I think the graph that we are talking about is a sine function that looks something like this, where this is the values of 0. Okay, so I just label here as 0. So this is a sine function. If you extend this, the sine function would look something like this. So I'll label this as y equals to sine theta. Okay, so we want to know what is the limit of sine theta when theta goes to 0. So we answer these questions by using the sandwich theorem. So what are the two functions that sandwich the function sine theta? Right. So the function that we can think of is actually the function of y equals to absolute values of theta as the function above sine theta, and the other function is the reflections of the absolute values of theta about the x-axis. So this function, if you represent it onto the graph, it will actually look something like this. Okay, so this is the function of y equals to theta. So maybe I should label these functions with a different color. Okay, so let me try to rub this off and use a different color to represent the absolute values of theta. So the graph for y theta is like this. Okay, so this is y equals to theta. I think this is kind of straightforward and understood because theta is always larger or equals to sine theta. You agree about that, right? So for theta, which is close to 0, this is always true. This is for values of theta, which is close to 0. Okay, I think not only is close to 0, I think it's generally quite true. It is particularly correct for the regions of theta that is lying around theta equals to 0. Okay, so if you were to label or draw the function of y equals to negative theta, that is what you get. Okay, it is like this. So this is a function of y equals to minus of absolute values of theta. So now we have found two functions that sandwich the sine theta. The upper function is absolute values of theta. The downstairs function is minus absolute theta. So we have already found the function of h and g that fulfill this criteria. Within some values of theta that includes 0 value, sine theta is always sandwiched between this function and this function. And it is quite obvious that the limit of the absolute values of theta and the limit of the negative values of theta when both theta tends towards 0 when theta tends towards 0 are just equals to 0. So these are the common limits of the upper function and the lower function. Since y of sine theta is always sandwiched between minus theta and is larger than minus of absolute theta and is less than the absolute of theta. And in addition to that, the two upper and lower functions converge to 0 at the limit of 0. Then, according to the sandwich theorem, the limit of sine theta when theta tends to 0 is then simply equals to the common limit of the sandwiching theorem of absolute value of theta, then this is just equals to 0. So revisions of these tricks, in order to prove the limit of sine theta at the point theta is 0, you find the upper function of absolute values of theta and negative values of theta, and these two always sandwich the sine theta between some values of theta that enclose theta equals to 0, and on top of that the upper and lower functions converges to a common values of limit which is 0, and then by the virtue of sandwich theorem, the sine theta limit is just equals to the limit of the sandwich theorem of absolute theta, which is 0. So that is the graph for y equals sine theta sandwich between absolute values of theta and the negative values of absolute theta. So you can also try to understand the limit of the function of, say, 1 minus cos theta. So if you're asked to calculate the limit of 1 minus cos theta at the point theta tends towards 0, you can also use the sandwich theorem, right? So the definitions of cos theta is always lying, right? The cos theta is always lying between what? It's lying between minus 1 and plus 1, okay? So if you take the values of 1 minus cos theta, okay? 1 minus cos theta, the values of 1 minus cos theta is always larger or equals to 0. Can you convince yourself that this is always the case, right? So because cos theta would never be larger than 1, right? So 1 minus the largest values of cos theta would always be positive, okay? And cos theta could also become negative. When it becomes negative, 1 minus cos theta would also be a positive number. So it is always true that 1 minus cos theta is always larger than 1. Then what else? 1 minus cos theta is always, I can prove that it's always equals or smaller than the absolute values of theta. Okay, so if you were to represent this on a graph, then you see that this is the cos 1 minus cos theta, and this is the values of y equals to 0. This is the values of y equals to theta. So we have found two functions that always sandwich y equals to 1 minus cos theta between some values of theta that includes the values of theta at 0. Furthermore, the upper function of absolute values of theta at the point theta equals to 0 is the same as the functions that lies below 1 minus cos theta at the limit theta equals to 0. And this lower limit, well, this lower function, which is always below 1 minus cos theta, is a constant function called y equals to 0, right? So for the constant function of y equals to 0, the limit is always equals to 0, right? So both function limit is 0 at the point x and the point theta equals to 0. So by virtue of the sandwich theorem, the limit of 1 minus cos theta and theta tends to 0 is proven to be 0. This 0 is the common limit of the upper function and the lower function, okay? So here you learn the tricks that in order to prove the limit of a function at a point using the sandwich theorem, you have to be able to come up with upper and lower functions such that it always sandwich the function under consideration within some intervals that includes the point of the the point of C where you want to evaluate the limit. And furthermore, the limit of the upper and lower function has to be having the common limit at the point C. So here sometimes the sandwich theorem is not quite easy to use because you have to come up with the upper and lower function, and it's not always able to prove the limit of a function using sandwich theorem. So only very specific function that you can use sandwich theorem to prove its limit. However, we are going to use the limit theorem, the sandwich limit theorem, again and again in the subsequent lecture. So that is the part on the sandwich theorem. So we'll stop here.